The first quantum number is the principal quantum number n. It describes the energy of an electron and the most probable distance of the electron from the nucleus. Like we saw before, we give them the numbers 1, 2, 3, and so on. The second quantum number is the angular quantum number or orbital quantum number that describes the subshells. The number of subshells is equal to the value from 0 to n-1. For example, for n equal to 3, there are 3 subshells, 0, 1, and 2. The third quantum number is the magnetic quantum number. This number describes the shape of orbitals in the space. For example, s orbital is spherical, p orbitals is dumbbell-shaped, and 4 of the 5 d orbitals are clover-leaf-shaped, and the 5th d orbital is shaped like an elongated dumbbell with a donut around its middle. The magnetic quantum number, ml, has values ranged between -L to L. The last quantum number, spin quantum number ms, describes the angular momentum of electrons with a magnitude +½ for electron spins around the axis clockwise and -½ for electron spins around the axis anticlockwise. We use quantum numbers to describe the distribution of electrons of an atom or molecule in atomic or molecular orbitals, electronic configuration. For example, 1s2, the one here on the left, represents the principal quantum number n. S is the name of the subshell, and the number on the top right is the number of electrons in this subshell. Let's look at this exercise. What are the total number of orbitals for M shell? M shell, or M level, is the third level. You have K, L, then M. The M level is divided into 3 subshells, so this one is actually divided into 3 subshells. So first, the principal quantum number is equal to 3, then the L runs from 0 to 3 minus 1 is equal to 2. This means I have the angular momentum runs from 0 to 2. I have 0, 1, and 2. The subshell notation is S, P, and D. Notice that whenever I have the angular momentum 0, I will have the subshell S, and for 1 it is B, and for 2 it is D. The magnetic quantum number runs from -L to +L. This means for 0 it is equal to 0. For 1 it is -1, 0, and 1, because here I will just substitute the L with 1. Now I need for the 2, I will substitute the L with 2. So it runs from -2, -1, 0, 1, and 2. Now if I look at the number of orbitals, for S I have 1 orbital, for P it is divided into 3 orbitals, and for D it is divided to 1, 2, 3, 4, 5 orbitals. The sum of the 1 plus 3 plus 5 is equal to 9. So M shell contains a total number of orbitals equal to 9. So let's summarize it. For M shell, it is the third level. So it is divided into 3 subshells. The 3 subshells are S, P, and D. The S contains 1 orbital, P contains 3 orbitals, and D is divided into 5 orbitals. Each one of them can take up to 2 electrons, so I have S can take up to 2 electrons. P, it can take 1, 2, 3, 4, 5, 6 electrons. And D can take up to, I have 5 orbitals, each one of them can take up 2 electrons, so I have total of 10 electrons. So D can take up to 10 electrons. Remember when we said that each level is filled with a total number of electrons equal to 2n squared. So if you apply to this one, I have 2, and this is multiplied by the m, which is the third level, to the power 2 is equal to 9 by 2 is equal to 18 electrons. This is the same number here you can find if you sum the electrons of all orbitals. You have 2 plus 6 plus 10 equal to 18 electrons. So this is another way of looking at the electrons that fill the m orbital. I will leave a link at the end of the video and in the description of the video that talks about quantum numbers in details with examples. Let's look at another example. List the n, l, and ml for the 4d orbital. First, n equal to the number on the left, 4. We deal with the d subshell, so L is equal to 2, and ml has values from minus L to L. Therefore, the ml possible values are minus 2, minus 1, 0, 1, and 2. Like we saw before, arrangement of electrons around the nucleus is represented using electronic configuration. On the right, you can see the order subshell notation of electronic configuration 1s, 2s, 2p, then 3s, the order of filling from top to down. There are rules in filling these subshells that have to be followed. The first rule is called the Aufbau building up principle. The rule states that subshells are filled in order of increasing energy. For example, 2p is filled before 3s because it is less in energy. The second rule is the Pauli exclusion principle. The principle states that each orbital picks up to 2 electrons only, and their spins are in opposite directions. So, for 1s it has one orbital that can take up to 2 electrons only, and the 2 electrons spin in opposite directions. The third rule, Hund's rule, is related to the filling of orbitals. According to this rule, all orbitals in the subshell are singly occupied by 1 electron before doubling happens. Here, the example on the left, electrons are doubled before filling the third p orbital. This is why it is wrong. Also, all single electrons should spin in the same direction. Here, the middle example, the third orbital has opposite direction to the other 2 electrons. That is why we rule this one out as well. The example on the right shows the right electrons distribution according to Hund's rule.